Swayam Prabha. Digital India. Educated India.
Okay, so welcome to the next class. So last time I'll just quickly recap. So last time we started the formalism of thermodynamics, where we argued that like we did in kinetic theory, where we were interested in the microscopic dynamics of individual molecules, we are totally going to ignore that, and we are only interested in thermodynamic variables like pressure, temperature, volume, density, and so on. Okay, so that is like the underlying basis of this formalism of thermodynamics. All right, and we also kind of went through the concept of heat and work, and we also derived or we also looked at what's the statement of first law of thermodynamics in this formalism. So maybe I can like quickly write few things. So basically in thermodynamics, so we ignore microscopic details, right. So this is the underlying postulate or underlying most important concept of thermodynamics, that we are not interested in the microscopic details, and we are only interested in macroscopic parameters like temperature, pressure, volume, density, and so on. Okay. And we also wrote down the statement of first law of thermodynamics. According to which the change in internal energy of a system is basically the amount of heat provided or extracted from the system plus the amount of work done on the system or done by the system. All right. And we also wrote down its another form which was written in differential form, which is du equals dq plus dw. And we also like went through the reasons why we have put these cross on d, because we also argued that heat and work are not really state variables. Okay, so they are not functions of state. On the other hand, the internal energy is function of state. Okay, and we also wrote it down in this way, which is dq minus pdv, where p is the pressure on the system and dv is the change in the volume, and which basically corresponds to the work done by the system or on the system, depending upon what is the sign of the dV, right. So if your dV is negative, which means the surroundings are doing work on the system, in which case it will contribute to the internal energy. On the other hand, if dV is positive, the system is doing work on the surroundings and its contribution to internal energy will be negative, right. So we went through all these things. All right, and we also basically defined a very important quantity which is known as heat capacity, right, and we denoted it by symbol C, which was basically delta Q by delta T, and all it means is so heat capacity basically tells you how much heat is required to raise the temperature of a system by certain degrees. Certain degree, right. So if the delta Q heat is required to raise its temperature by delta T, the ratio is basically the heat capacity. All right, and we also saw that this can be achieved in two situations. Either the system can be at the constant pressure, in which case we call it the heat capacity at constant pressure, which is del Q by del T, and the symbol that we note is at constant pressure, right. And similarly, we can do this process at constant volume, in which case this is del q by del t at constant volume, right. And we also physically argued that Cp is always greater than Cv, right, because if we are doing a process at constant temperature and when we supply heat into the system can always do work on the surroundings, in which case part of heat is wasted in doing work on the system on surroundings. Therefore, we need more energy to raise the temperature of the system by the same amount. Okay. So, therefore, Cp is always greater than Cv. So, today what we will basically do is we will basically apply the statement of first law of thermodynamics to basically just check whether we can find an expression for the difference between Cp and Cv, all right. So, essentially what we are going to do today is applying first law to determine the difference between heat capacity at constant pressure and heat capacity at constant volume. Okay. So basically okay, so let us get started. So, consider we have a system. So, consider a system whose internal energy denoted by U is basically a function of temperature and volume, right. So, internal energy is basically the total energy in the system, right, and it is sum of the kinetic energy and the potential energy. So, in general it is temperature, it is function of temperature, which basically determines how fast the individual gas molecules are moving in the system, and the volume, which determines how far away from each other these molecules are, which in turn determines the potential energy, right. So, in general the internal energy of the system is a function of temperature and volume, all right. So, therefore, from this functional form we can write down the differential u which is as follows. So, this is partial derivative of u with respect to T computed at constant volume times the differential of temperature plus del u by del V computed at constant temperature times dV, right. So, this is the total differential of the internal energy. But remember from first law, so from first law, so we saw that du is nothing but dq minus pdv, right. And again remember I am putting a cross sign on dq because it is not an exact differential, all right. And from here I can simply write the dq is basically du plus pdv. Okay. So, what we will do is, so let us call this equation 1, let us call this equation 2. So, we will substitute equation 1 du from equation 1 in equation 2. So, basically substitute 1 into equation 1 into, right, and therefore, we can write the differential in heat basically becomes del u by del t at constant volume times dt plus del u by del v at constant, sorry, I should be little bit more careful. So, this is v, this is u at constant temperature plus dV plus pdV, all right. And I will just okay. So, the next thing that we will do is we will basically differentiate this equation, both sides of this equation with respect to temperature at constant volume, right. So, basically differentiating both sides with respect to temperature at constant temperature, constant pressure, all right. So, therefore, this becomes del q by del t at constant pressure is basically del u by del t at constant volume. So, this becomes 1 plus del u by del v at constant temperature times del v by del t at constant pressure plus p times del v by del t at constant pressure, Okay. And I'll just rewrite it in a slightly different form. I'm just going to rewrite the right hand side as follows. So, this is basically del u by del t at constant volume plus, so I will take del u by del v by del t, which is common. So, this becomes del u by okay, so maybe so times p plus del u by del v at constant temperature times del v by del t at constant pressure. And remember, the right hand side is del q by del t at constant pressure. Okay. But now remember, what is del q by del t at constant pressure. So, this by definition is nothing but heat capacity at constant pressure, and this is I will argue that this is nothing but heat capacity at constant volume plus P plus del u by del v at constant temperature times del v by del t at constant pressure. And okay, so and why did I say that this is CV? So, that is because by definition CV is nothing but del q by del del q by del t at constant volume. But remember from first law. So, from first law, for dV equal to 0, which means at constant volume your du is nothing but it is simply equal to dq, right, because your PdV term is 0, right. So, remember in first law, if I just put dV equal to 0, then your du is basically dq, and therefore, in this case this just simply becomes del u by del t at constant volume. Okay. So, therefore, I can just replace this term with CV, and from this equation we can basically write down the final expression for Cp minus Cv, which is given by P plus del u by del v at constant temperature times del v by del t at constant pressure, right, and this is what this is kind of the final expression that we were after, right. So, basically what we have done is we earlier argued just from the physical intuition that Cp should always be greater than Cv, but now we have applied the first law of thermodynamics to basically find out an expression for the difference between heat capacity at constant pressure and heat capacity at constant volume. Okay. So, basically maybe I can rewrite this. So, let us try to understand this equation, right. So, remember there are two important terms in it, right. So, first term is let us analyze the first term first, right. So, which is del u by del v at constant temperature, right. So, what does it mean? So, this means what is the change in internal energy with respect to the volume of the system, okay. And so, remember let us consider an ideal gas, right. So, I remember we said that in ideal gas the internal energy contribution only comes from the kinetic energy, right. So, therefore, the volume, which in turn tells you the intermolecular distance between the molecules, it should not really play any role, right, because the only contribution to the total energy is coming from the kinetic energy. So, therefore, we argues that del u by del v, and provided we are fixing the temperature, the changing the volume of an ideal gas does not really change its internal energy, and this is 0 for an ideal gas, right. So, that is first thing that we can already say about this term del u by del v at constant temperature, right. But what about a real gas, right. So, this is for an ideal gas, but but for a real gas, so remember what is a real gas. So, remember when we did the van der Waals equation of state, the real gas equation, we said that now the molecules are free to interact with each other, right, and we argued that the typical potential is always it looks like this, right. So, this is the potential energy, this is the 0 of the potential energy, this is 0 of the potential energy, and this is some typical spacing between molecules, right. And in equilibrium the molecules tend to stay at certain equilibrium separation, which is R0, right. So, but now what we are saying is, so we are interested in calculating the quantity like del U by del V, the variation of internal energy with respect to the volume, keeping the temperature constant, right. So, basically what we are doing is we are expanding the system, we are increasing the volume of the system. And what happens when we increase the volume of the system? Basically the average intermolecular separation, that also increases, right. So, therefore, the two molecules which were sitting at this value of potential energy, which is a negative value, they climb somewhere here, right. When we increase the volume, the intermolecular spacing increases. So, the contribution to the internal energy comes from the quantity which is now less negative, and remember the internal energy is now sum of the kinetic energy and potential energy, and just by increasing the volume of the system, we are now adding a smaller value of a smaller negative value to the total energy, to the internal energy, right. So, therefore, essentially, so upon increasing volume of a real gas, right, U also increases, right. And why? Because remember U is the contribution to U comes from kinetic energy and potential energy, and since we are increasing the V, we are increasing the intermolecular separation. So, we are adding a smaller negative quantity to the total internal energy, and therefore, U also increases. So, therefore, we can say that del U by del V, keeping the temperature constant, is always positive for a real gas. Okay. So, hence combining both these things, we can say that del U by del V, this quantity that we are analyzing at constant temperature, is either greater than 0 or equal to 0 for any gas, right, for any gas. Alright. So, that is the first thing that we have learned. And now what about the other quantity, right. So, we have now talked about del U by del V at constant temperature. Now, let us talk about del V by del T at constant pressure. Okay. So, del V by del T at constant pressure. Okay. And again, like it is very simple, right. So, what you are doing is you just have to now visualize or imagine the system, right. So, you are given a system whose pressure you are fixing, right, and you are now increasing the temperature of the system, right. So, basically you are in some sense pumping energy into the system, the kinetic energy of the molecules is increasing, and again, like this is why the kinetic theory picture becomes useful. So, you just have to imagine a box, maybe I can draw. So, you just imagine a box whose pressure is fixed, right. So, say this is a piston, right, and the initial volume is V, right, and what we are doing is we are increasing the temperature by a certain amount, and what that does is that basically increases the kinetic energy of these molecules, right. These molecules are now moving much faster since we are increasing the temperature, and they are imparting greater and greater amount of momentum onto this wall, and therefore, the system will tend to expand, right. So, this is very natural for it to happen, right. More energy you pump, the more so there will be more net transfer of momentum and system will tend to expand, right. So, therefore, del V by del T at constant pressure has to be greater than 0, right. So, by virtue of increasing the kinetic energy of molecules, the system will always tend to expand because we are keeping the pressure constant, right. So, therefore, if now we again go back to this expression, we argued that this del U by del V at constant temperature is always either 0 or greater than 0, and del V by del T at constant pressure is always greater than 0. So, we can clearly see that this quantity can never be negative, right. So, therefore, Cp minus Cv is always greater than 0, always, right. So, basically we got back to the previous result that we physically argued that the heat capacity at constant pressure is always greater than the heat capacity at constant volume. Okay. But now let us maybe try to evaluate the value of Cp minus Cv for an ideal gas, right. So, that is what we have been discussing in detail throughout the course. So, let us do that. Okay. So, next thing that we will do is the value of Cp minus Cv for an ideal gas. Okay. So, say consider we have, so consider n moles of monoatomic ideal gas. Okay, so, this is important. So, I will not really go into the details here right now, but let us assume that this is monoatomic, right. So, there is just one atom. So, there are basically the reason we are saying is there are only 3 degrees of freedom associated with every molecule. Okay. So, say our ideal gas is a monoatomic ideal gas right now. Okay. So, in this case, since it is an ideal gas, its total internal energy, or maybe we can just write the internal energy. What is the internal energy of an ideal gas? That is just the sum of kinetic energy of all the gas molecules, right. So, basically that is N, which is number of moles, times Na, which is the Avogadro number, which is, and this basically tells you the total number of gas molecules we have, times the average kinetic energy of individual gas molecule, right. So, half mv RMS squared. Okay. And remember we saw that this is basically exactly equal to N A times N times 3 by 2 kBT, right. That is like the kinetic interpretation of the temperature, and this is as you can see, this is just the total kinetic energy of all gas molecules. Okay. And again we can, okay, so and this internal energy is denoted by symbol U. So, clearly del U, so the first term which is del U by del V, right, del U by del V at constant temperature is 0, right, because there is no volume term in this equation, right. So, if you just take partial derivative of this U with respect to V, keeping the temperature constant, you will get 0. Okay. Okay. And now what we are, so basically we are interested in evaluating this quantity for an ideal gas. So, we just argued that del U by del V for an ideal gas is 0. So, now let us see what is del V by del T, right. So, that is the first term. So, what, so remember the equation of state for an ideal gas is as follows. So, PV equals nRT, right. This is the ideal gas equation, in which implies we can write our V as nRT divided by P. Okay. So, from here we can see that del V by del T, this is the term that we are interested in, at constant pressure is nothing but N R divided by P. Okay. So, what we will do is now we will just substitute del U by del T, del V at constant temperature and del V by del T at constant pressure back into this equation, and we will see what we find, what we get, right. So, therefore, Cp minus Cv is basically equal to P plus 0, right, times Nr by P, right. So, this is the Nr by P that we got here, and you can see here this is basically equal to N times R. Okay. So, therefore, this is our final result for n moles of ideal gas, of monoatomic ideal gas. Okay. Our Cp minus Cv is essentially just Nr. Okay. So, that is the first result that we have. But let us see if we can do more. right. So, remember our internal energy. So, remember the expression for internal energy that we got was so 3 by 2. So, I am just rewriting this. So, 3 by 2 kBT times Na times N, right. So, 3 by 2 kBT times Na times N, right, and this I can just rewrite as, so remember Na is Avogadro's number, Kb is the Boltzmann constant. So, the product of these two is the gas constant. So, this is basically 3 by 2 N RT, right. So, therefore, we can define the heat capacity at constant volume, right, which by definition is del Q by del T at constant volume. But we saw that when the volume is kept constant, the change in internal energy is exactly equal to the change in heat, right. So, this we can simply write as del U by del T at constant volume, and if we take derivative, this just becomes 3 by 2 N R, right. So, essentially for an ideal gas, we can very simply evaluate the heat capacity at constant volume. Okay. So, what we will do is we will now substitute this value C V in this equation. So, therefore, from this equation we can see that C P is C V plus N R, which is 3 by 2 N R plus N R, this is 5 by 2 N R, right. So, therefore, so we have basically evaluated few important quantities. So, the difference between heat capacity at constant pressure and volume for an ideal gas is Nr. The heat capacity at constant volume for an ideal gas is 3 by 2 times Nr, and heat capacity at constant pressure is 5 by 2 Nr. Okay. And there is another useful quantity that we can define, which is known as adiabatic index. And this is denoted by symbol gamma, and this is equal to the ratio of heat capacity at constant pressure and constant volume. And you can very easily see that in this case for an ideal gas, this is 5 by 3, right. So, because Cp is 5 by 2 Nr, Cv is 3 by 2 Nr, so that ratio is 5 by 3. Okay. This is for a monoatomic ideal gas. Okay. So, and another small thing is basically since adiabatic index already takes care of it involves the ratio of heat capacities. So, this is also equal to the molar heat capacity, right. So, C small c by small v. So, remember molar heat capacity is heat capacity divided by the total number of moles of gas, right, and adiabatic index for an ideal gas is, when written in terms of the specific heat, right, that is also 5 by 3. Okay. So, before we basically take a little bit detour, I will just try to define another quantity which will anyway go back in little bit detail, which is known as latent heat. Okay. So, latent heat. So, I will just briefly mention what it is, because it is related to what we have been discussing so far. Okay. So, remember so far we have been defining the heat capacity as change in temperature upon providing certain heat to the system, right. So, so what we are saying is, when we provide some heat to the system, its temperature changes, right, it rises. But it so happens that in certain situations, even if we provide heat to the system, its temperature does not change. Okay. So, what that means is, so in some situations for finite delta Q, delta T does not change, okay, delta T remains 0, in which case the heat capacity basically diverges, right. So, it loses its meaning in other way, right. We can't really define this quantity heat capacity, and I will basically just tell you that even though it sounds unreal, but it happens, and it happens when the system is undergoing a phase transition, okay, and we will go back to these details, and in which case this heat that we are providing for system to undergo a phase transition without changing its temperature is known as the latent heat, okay. So in this case delta Q is known as, is defined as latent heat, okay. So remember, there are situations where you provide heat to the system, but it is utilized in undergoing undergoing phase transition, say from liquid to vapor or something like that, right, and the temperature does not really change, and these situations will encounter when we will look at the thermodynamics of phase transitions, okay. All right. So, so what I will do next is I will basically go through the concept of reversibility and quasi-static processes again in a little bit of detail, okay. So, reversibility and quasi-static processes. Okay. All right. Okay. So remember we have been defining the work done. Okay. So we always draw a schematic like this, where we start with a situation where piston wall is somewhere here, right, and there is a pressure P, right, and the initial volume is V, but after some time the wall moves here, right, the wall moves here and the volume goes to V minus dV, all right, and the change in the volume basically is dV. So, change in volume is dV, and we say that the work done, which is delta W, is basically, or I can just write work done equals minus P dV, okay. And we again, I will repeat, and we say that if dV is negative, dV is positive, that means work done by the system, and if dV is positive, right, then work done on the system, okay. So, on the system, okay, in this particular situation, okay. All right. But remember, when we write this expression, we are assuming that the pressure does not change when the volume of the gas is changing by an amount dV, okay. So, now I just want you to like just think about it, right. So remember, so say we start with a certain volume, okay. So, let us start with a certain volume V, in which case the pressure is maintained at P, right. And now in the second case, when the pressure when the volume goes down, say V minus dV, okay, we know that for an ideal gas, the pressure basically scales inversely with volume, right. So, if I decrease my volume, the pressure is bound to go up, right, and you can now basically raise an argument that how can we claim that the pressure remains constant when the volume is going down, because we know pressure and volume are related to each other, right. So, so what I am saying is, so when we define the work done as minus P dV, we assume P to remain constant, right, while the system's volume changes by an amount dV. But we know that from ideal gas equation that is not physical, because when we change the volume, the pressure changes, right. So, so how do we get out of this dilemma, right? So, basically we basically say that the process happens quasi-statically, and what does it mean? So, that means we are changing the volume of the system by such a tiny and extremely tiny event that we can assume that the pressure is more or less constant, right. So, basically for a quasi-static, so that is how the concept of quasi-static processes evolve. So, we say so basically so therefore, we come up with the concept of quasi-static process, quasi-static process. The change in volume is so small that it basically tends to 0, such that the pressure remains constant. And remember, what we are doing is we are changing the pressure, the volume of the gas from certain initial volume to some final volume, and we are doing it in increments of dV, which are extremely small, just to ensure that the pressure of the gas for that particular process does not change, right, it remains constant, right. And therefore, you can now imagine, in order to basically basically do this process, we have to do this process at extremely low rate in increments of dV, which are almost equal to 0, right. So, therefore, this concept of quasi-static processes comes into the picture, right. So, that is and basically, and the meaning of quasi-static is basically almost static. Okay. So, it is extremely slow process. Okay. Okay. And only then we can define, we can write down the functional form of work done as P times dV. Okay. Otherwise, it is not possible. Okay. And the other word that we basically used is reversibility. Okay. So, what is the meaning of reversibility? Reversibility. So, now let us say we have a situation, okay, where you have these gas molecules which are everywhere, okay, and say we expand this gas, okay. So, we expand it, or quick expansion. Quick expansion. And when I say quick expansion, that means we are breaking the condition of quasi-static condition, right. So, in that situation, the process will look something like this. So, what we are doing is we are moving the piston so fast, okay. So, I just want you to use your imagination. So, I moved the piston so fast that gas molecules have absolutely no time to react to that, right, and there is basically a void, right. So, basically what I am doing is I am expanding the system from the wall from this point to this point, and it is happening at such a high rate that there is a void that has been created, right, and in which case the pressure is not really defined, right. So, since there are no gas molecules here, they are not really imparting momentum to the wall. So, the instantaneous pressure is not really it is basically 0 in this extreme situation, right. But eventually later, right, after we wait for very long time, these molecules will diffuse around, right, and they will again occupy this entire volume, right, in which case the pressure, okay. So, let me call this P1, let me call this P2, and let me call this P star, okay. So, what we are doing is we are making the system go from a state 1 to 2, in which case the pressure P1 is well defined because it is at equilibrium, the molecules are hitting the wall and they are imparting the momentum, in which case we can define the quantity pressure, which is a rate of change of momentum per unit area per unit time, right. And also at later stage, when the volume is different, there is a different pressure, but if we are doing this process very quickly, not quasi-statically, the intermediate pressure is not really defined, right, because there are no gas molecules which are hitting on the wall. and therefore the pressure is not really defined. Okay. So therefore, now imagine, right. So say this process is happening in this direction. Okay. But remember, if I play, okay, so say I record the video of this process and I play this backwards, right. Now see what will happen. So you start with the state where all the gas molecules are here, but spontaneously they all move into the one corner of the container, and then immediately the piston moves in, right. And you can see that this is counterintuitive, right. The gas molecules can't really move into one corner of the system spontaneously, right. So basically if I play this process backwards, they are indistinguishable, right. Sorry, they are distinguishable. So you can tell the difference between what is a real process and what is not a real process, right. So therefore such a process is irreversible, because we can tell the difference between the forward and the backward process. But now imagine on the other hand, we are doing this process quasi-statically, that we are moving this piston wall ever so slowly, that the pressure is always well defined, right. And if I do it in the small increments of dV which are approaching 0, then if I play that video backwards, then you will not be able to distinguish between forward and backward process, in which case it will be known as a reversible process, right. So maybe so what I can say is okay. So for a fast process, right, which is not quasi-static, forward and backward processes are not indistinguishable. And which I just argued, that in which case the intermediate pressure is not really defined, right. It is not really in equilibrium, this is driven out of equilibrium, right. And in this case this is an irreversible process, reversible process, right. And and what it means is intermediate states are not in thermodynamic equilibrium. But on the other hand, for a quasi-static process, right, forward and backward processes are indistinguishable. Right, in which case maybe I can write here, in which case this process is basically reversible and the system remains in equilibrium throughout the process. Okay. So I hope this important concept is clear to you. All right. So therefore what we can do is we can define okay. So now let us go back to the definition of pressure, right. So remember we were defining our pressure in this way. So this is pressure, this is volume, and our system is changing from an initial volume Vi, or let us call this Vf, does not matter. So this is Vi to Vf, right. And for a quasi-static process we assume that the pressure does not change as okay, and the work done in such a case, okay. So the work done, which is delta W, which is minus P times dV, that simply becomes minus T times Vf minus Vi, okay. And this is if pressure is constant. that is true only if and only if Vi is almost equal to Vf, okay, if the process is happening quasi-statically, okay, and this is certain constant pressure P. So, this is the constant pressure, the value of constant pressure P. But remember, like in general the processes occur according to certain equation of state, right, and we already know for an ideal gas the pressure and volume, they follow what is known as an isotherm, right, and the pressure basically decreases as we increase the volume, okay, and say we start from certain initial volume Vi and we go to certain final volume Vf, okay. And in which case, in this case what we have to do is, since pressure is not really staying constant, we can divide this pressure into multiple steps of multiple quasi-static processes, right. So, we can divide this Vi minus Vf into small increments of dV, right. So, this is dV, where we can assume that the pressure is constant over that particular increment, and the value of that pressure actually is given by the equation of state of that particular system, right. So, in this case the work done will be minus, and we will basically integrate this out from Vi to Vf times pressure, which is now function of volume, times that increment dV, okay. And this is how we can define the work done from say changing the volume of the system from Vi to Vf using the concept of quasi-static and reversible processes, okay. So, in the next 5 to 10 minutes what we will now do is we will use basically this concept to understand the compression of an ideal gas, okay. So, let's compress an ideal gas. Okay. So, basically what we are doing is we are given a gas which is at certain volume V, right, and we apply some pressure and we move the piston wall in such that the volume goes from V to V minus dV, okay. So, basically V, so the volume goes from V to V minus dV, okay. So, we can do this process in two ways. So, first is isothermally. And what do I mean by that? So, what we do is we attach our system to a huge reservoir. There is another new definition that we have come up with, reservoir. So, this is just a huge system whose temperature or whose thermodynamic quantities do not really change, right. So, our system is much smaller than the reservoir, and this reservoir is kept at certain temperature T, and if certain heat goes into this reservoir, it is such a huge system that, I mean, the reservoir itself is a system which is so big that any amount of heat that goes into it does not really change its temperature, okay. So, basically what we do, we compress the ideal gas from Vi to Vf, right, Vi to Vf while maintaining its temperature or keeping its temperature constant at constant temperature T, okay. And in this case what will be the work done? So, remember this definition that we just wrote. So, this is delta W equals minus P Vi to Vf P, which is a function of V times dV, right, and we know for an ideal gas. So, for ideal gas, so P, which is a function of V, is basically N kBT divided by V, right, and we just substitute this back here. So, our delta W becomes negative of Vi to Vf n kBT divided by V times dV, and if you just evaluate this integral, this simply becomes minus n kB T log of Vf by Vi, and if we want to absorb this negative sign here, this becomes n kBT log of Vi by Vf. Okay. And we can see since Vi is greater than Vf, so remember we are compressing the gas, so initial volume is always greater than the final volume. This implies our delta W is positive, which means we are doing work on the system. So remember that was the notation that we have been using. So when work is done on the system, we get a positive sign. Okay. And also we can very trivially see that from first law, from first law we know delta U is delta Q plus delta W, right. But we know that for an isothermal process, delta U is 0, right. If we do not change the temperature, the internal energy of an ideal gas does not change, which implies your delta Q is basically nothing but negative of delta W. So therefore we can write our delta Q is n kBT log of, so these things will, this Vi and Vf will switch, right. So Vf by Vi, right. And also here we can see since Vf is less than Vi, our delta Q is negative. And what does that mean? So when we compress the system, we decrease its volume, the heat is released from the system into the reservoir, right. So we are doing work on the system, from externally we are doing work on the system, there is heat production in the system which basically leaks into the reservoir such that its temperature does not change, right. So therefore we do work done on the system, so heat, so this means heat released into the reservoir, right, such that the temperature of the gas remains constant. Okay. So these are some things that directly come out of this. Okay. So that was the isothermal compression. So let us compress the ideal gas adiabatically, right, adiabatic compression. Okay. And the meaning of this word adiabatic is we are keeping the heat constant. Okay. We are not letting system to leak out or to change its heat. Okay. So how do we do that? So again we have this system, okay, and rather than putting in contact with the reservoir, we insulate it. Okay. So let me draw it properly. So we insulate it. Okay. This is how we denote insulation. How we schematically show insulated system. Okay. And there is certain pressure P which takes its volume from Vi to Vf, where Vf is less than Vi. Okay. Okay. So adiabatic implies no heat exchange allowed. Okay. So therefore again we can write down the first law, right. So from first law we can write del U is del Q plus del W, right, and since we are saying that delta Q is 0 for an adiabatic process, and this implies our del change in internal energy is basically equal to the amount of work that we are doing on to the system. Okay. And also since by definition the heat capacity at constant volume is del Q by del T, but at constant volume we can just write down it as del U by del T, right, at constant volume, and this implies our du is basically can be written as Cv dt. Okay. So let us call this equation number 1. Okay. And also for a quasi-static process, okay, so also for a quasi-static process, dW equals minus PdV, okay. Right. So basically what we are saying is our du is equal to dW, so which I can just write. So dW is equal to CV dt, right, and also here our dW is minus PdV, right. So basically just equating the, so let us call this as equation 1 instead, right. So this is equation 1, this is equation 2. So equating 1 and 2, we can write CV dt equals minus PdV, right. And for the ideal gas, pressure is nothing but minus n kBT divided by V times dV, okay. And I am just rewriting it in this way. So what is the total number of gas molecules? That is number of moles times Avogadro number times kBT divided by V times dV, and this quantity is the gas constant, right. So this is minus nRT by V dV, and this is CV dt, okay. All right. And remember what is happening, right. So we are doing work on the system, and since it is not in contact with any reservoir, heat exchange is not allowed, the temperature of the system is bound to increase, right. So upon compression from Vi to Vf, temperature increases from Ti to Tf, okay. So therefore we can integrate this equation out. So what we can do is Cv dt, the temperature going from Ti to Tf, remember system is heating up now, and this is minus Nr minus Nr, okay. So I can move this, so what I have done is I have moved this T here, okay. So this goes from Vi to Vf times dV by V, okay. And if we integrate this out, so we get Cv by R, I am moving R on the left side, log Tf by Ti is equal to minus n log Vf by Vi, okay. And to get rid of this minus sign, so we get Cv by R log Tf by Ti equals n times log Vi by Vf, okay. So this is what we got. But remember earlier in the class we saw for an ideal gas Cp minus Cv equals Nr, okay. This is what we derived for an ideal monoatomic gas, right, monoatomic gas, okay. And also we saw that gamma, which is the adiabatic index, gamma is defined as Cp divided by Cv, okay. And from these two equations, so if you just divide this equation by Cv, so we get so gamma minus 1 equals Nr by Cv, okay, which implies Cv by R, I am just rewriting it in this way. So Cv by R is n divided by gamma minus 1, okay. And why we are doing this? Because we are basically trying to get this quantity Cv by R, okay. So now we will just substitute this Cv by R by n divided by gamma minus 1. So therefore n by gamma minus 1 log. So, I am just substituting here Tf by Ti is equal to n times log Vi by Vf. Okay. And n cancels out, and what we get finally is log Tf by Ti is gamma minus 1 times log Vi by Vf, and we can now remove log from both sides, and this basically becomes Tf by Ti equals Vi by Vf raised to the power gamma minus 1, or this can be written as Tf Vf gamma minus 1 equals Ti Vi gamma minus 1, or another way to write this is T times V gamma minus 1 equals constant. Okay, so, that is an important result for an adiabatic compression of an ideal gas. But we can rewrite it in another in a slightly different manner, okay, which is actually more useful. Okay. So, now remember from ideal gas equation. So, from ideal gas equation, so we can write our temperature as PV divided by NR, right. So, what we can do is we can just substitute. Okay. So, what we can do is we can substitute Tf equals Pf Vf and Ti equals Pi Vi divided by Nr, and if we just substitute these values of Tf and Ti into this equation, so you can very easily check. What we get is Pf Vf times Vf gamma minus 1 equals Pi Vi times Vi gamma minus 1, or Pi Vi raised to the power gamma equals Pf Vf raised to the power gamma, or Pv gamma is constant. Okay. So, this is another interesting and important result that we get for an adiabatic compression. Okay. So, therefore, just to summarize, maybe I can write down final two equations. So, for an isothermal compression, we know that since it is at constant temperature, so the product of pressure and volume is constant, whereas for an adiabatic compression, so Pv raised to the power gamma is constant. Okay. So, yeah, so we will meet in the next class. Thank you.